This is the 17th session. So let us begin. Today we will begin with the exhibit circuits. Before that, let us have a brief recap of previous session. Previous session we have discussed the realization of OR gate using diode. Then we discussed about the NOT gate, the universal gates. We have discussed NAND gate, NOR gate, XOR gate, properties of XOR and XNOR gate. Then we revised the types of gates. So we have three basic gates: AND, NOT, OR, and two universal gates. Those are NOR, NAND, and NOT. So this is the classification. Apart from that, we have two special gates, XOR and XNOR. Total 7 gates. Now let us see the next topic. We'll see different circuits and how to make the circuits and how to realize the logic. Say we have gates like AND, OR, NAND, and NOR. These gates can be used to control the passage of an input logic signal through the output. Right? So what is meaning of control logic? For example, say we can make something like enable circuit. Say we'll use one AND gate, and at input A we will give some pulse, changing pulse, and B we will keep constant. Say B is equal to 1, and our main input we will give at A. So this is our input at A. So input is changing like 0, 1, 0, 1, 0. So what will be the output? At the output side, so we'll call output X. So if one input is 1, either this one is 0, what will be the output? Output will be, if this input is 0, for example, first one, 0, 1, output will be, if any one is 0, output will be 0. If input is 1, output will be 1. Again, if input is 0, output will be 0. That means what we can say, output is always equal to A. Whatever is input given at A, the same output is going to, whatever input given is at A, same output is given at going at B, because B is permanently set as 1. Right? So here logic A is applied to one input of each to this logic gate, and the other input of this gate is the control input B. So the logic level at this control input will determine whether the input signal is enabled to reach the output or inhibited from the reaching the output. Right? So that means this is a circuit who is enabling. This is enable. Now let us change the circuit and we will see. Say now same, we will take one diode, and now this time what we will do, we will keep B as fixed 0. Say X is our output, and as usual at A we are giving the input signal. Say input signal is same, our pulses in the form of zeros and ones. Suppose now first input is 0. So 0, 0, output will be 0. Now if input is 1, then output is equal to 0. Again, A is 1, B is 0. Output is again 0. So for all the inputs, output is permanently 0. That means what we are doing, we will call it as, this is not enabling, this is inhibiting. So this is inhibit logic. Okay, so now this is about the AND gate. Now let us see NAND gate. Now here I will take one NAND gate, so like this, AND gate followed by one bubble, and we have two inputs, say A and B. Here B is always 1, and at A we will give this pulse. Now we'll check the output at output X. What is the logic of NAND gate? It is opposite of AND. Suppose this is 0. First input is 0. A is 0, B is 1. For AND gate, it might be equal to 0, but for NAND gate, it will become 1. Now, if we give 1 here and B is 1, 1, 1 used to be 1 at the end of AND gate. Then NOT gate will again make it 0. Then again this input, if we make 0, 0, 1 will be equal to 1. So what is the output here? Now X is nothing but A bar. That means whatever input is at A, at output it is inverting A. Right? So that means it is enabling with some inversion. Now similarly, if we make B as 0, let us see what happens. Say we'll use one circuit like this. So this is our NAND gate. Two inputs A, B, X is output. Now this time we'll keep B equal to 0. Now B is equal to 0. A will change. Say A may be 0, 1, 0, 1 like that. So first, if we keep A equal to 0 and B is equal to 0. For AND gate it would be 0, but for X it will be 1. Now if we give 1 at the A is 1, B is 0. For AND gate it will be equal to 0, but for this it will be 1. Right? So for all the inputs, X is equal to 1. That is inhibit. Okay, so the same thing we can do for OR gate and NOR gate. Let us see. Now let us consider, say, OR gate. So we will take two input OR gate. Here we have two inputs A and B. Okay, B is, say, permanently we are keeping 0. We will check the output X. At A we are giving input pulse. So say A is 0, 1, 0, 1, 0, 1. So first if we give 0, A is 0, B is 0. If both of them are 0, X will be 0. Then A is 1, B is 0. Any one is 1, then output will be 1. Again 0, 1, same pattern will go on. Right? So what we can conclude here, if A is 0, output is 0. If A is 1, output is 1. That means logic is X is equal to A. Right? Now this is enabling. So as input is coming, it is going to output. Now let us change it for B input. We will change. So this is OR gate. Now at B equal to, we will keep permanent 1. This is our X. This is A. At A we will give the input signal. Say like this. So say if A is 0 and B is 1, output will be 1. If A is 1, B is 1, output is 1. That means X is always 1. Right? Now this is the case of OR gate. Now let us see the NOR gate. Now let us see for NOR gate. Let us draw the symbol of NOR gate. So these are two lines, input. This is OR followed by one bubble. Here we have A, and input signal we are giving at A. B we are keeping 0. There is output X. So let us see what happens with this. Now first, if A is 0, B is 0. When both of them are 0, OR will make it 0, but inverter will make it 1. Then this is 1, this is 0. OR gate will make it 1, but this inverter will make it 0. So what is happening? It is making the inversion. X is equal to A bar. If input is 0, output is 1. If input is 1, output is 0. So the logic of output is A bar. Similarly, we will see by changing the fix, we'll fix B as 1. Say this is NOR gate. A, now B will keep fix 1, output will get at X, and input signal we will give at A. If A is 0, B is 1. OR gate will make it 1, but NOT gate will make it 0. If input is 1, OR gate will make 1, 1, 1, but NOT gate will make it 0. That means the output is always 0, whatever may be the input. Here output is always 1, whatever may be the input. That means it is always on. No one can off it, either the signal is changing or not. This one is always off, irrespective of the input signal. Okay, now let us see one example. We will see the XOR and XNOR logic proofs. The next example. Our example is show that A XOR B is equal to AB bar plus A bar B. Let us solve this step by step. First, let us draw the XOR logic and what is its truth table. So this is XOR symbol. So first, we'll see what is XOR and its truth table. Say we have two inputs A and B. The possible inputs are 0, 0, 0, 1, 1, 0, and 1, 1. Right? These are the possible inputs. Now, for these inputs, for XOR gate, here I will draw the XOR gate. Say this is X and additional line XOR gate. These are two inputs A, B, and logic is A XOR B. What happens in XOR? If any one is 1, single one, then output, say our output is here A XOR B is 1. For if both are 0 and both are 1s, output will be 0. So it is 0, 1, 1, 0. Now what we have to show that this one, output for these two XOR is equal to this operation. So let us consider two lines. We have two inputs A, B. So I will draw two lines here. Say one line for the input A. So this is representing A line, and simultaneously we'll draw one line for, say, one for A, one for B. So this is A, this is B. First, if we consider this expression, AB, that means there is product. Product means AND gate. So we have to take AND gate here. One AND gate is required. So we'll draw one AND gate. One is output. Two inputs are there. One is A. So directly this A will be connected with AND gate. This is first input A. Second one is B bar. That means B we have to connect, but along with one inverter. So it will be B bar. Fine. So this is B bar. At the output, what we are getting here? Here we will get A, B bar. So this one is representing AB bar. Now we have to plus this thing. This AB bar we have to plus. Plus means which operation? OR operation. So this will go to OR gate. Right? This will be plus. But with whom? With the product of these two. Now these two are A bar B. So this is dot product. Sorry, this is product means we will use another AND gate. So where we require one more AND gate. So one is input is A bar. So now what we have to do? We will connect A with one inverter. So it will become A bar. And B is directly connected. So we'll connect it as B bar B directly. Now these both ANDs are OR. That means addition. So here we will connect with the OR. So this one is A bar B. And at the output of this circuit, what we have? We have AB bar plus A bar B. Now we will draw its truth table and we will see whether it is matching with this or not. So inputs A and B, we'll write here. First we'll give 0, 0, then 0, 1, 1, 0, 1, 1. And we will see what we get here at the output. Right? First we'll give both as 0. Say A is 0, B is 0. Now this 0 is going as it is to AND gate. And then this B is going as B bar. That means it is becoming 1 here. So for 0 and 1 AND gate, this output will be 0. Then here also 0 and 1 we are giving. This 0 will become 1 here. And for B 0, it will go as it is. So 1, 0 for AND gate, it is nothing but 0. Both the input 0 for OR gate, output is 0. So here output is 0. Right? Next one will give input as, next other input is, say we'll give 1, A as 0, B as 1. So now A is directly given 0. So it is going as 0. And B is 1. So after inverter, it will become 0. Both of 0, output will be 0. This is 0. Now here we are giving this A as 0. So here it will become 1 only. B is 1. So here input will be 1. Now this one is 1, this one is 1. Here output will become 1. So one input for OR is 0, another input for OR is 1. If any one is 1, output will be 1. So here we'll get 1. Third input we will give, say, third one will give this input, that is 1, 0. So A will become 1, B will become 0. So here we'll give 1 directly. So this one will become 1. Here B is 0. 0 will invert to 1. 1, 1 will become 1 here. Now this 0 will go with inverter. It will be 1 only. This B will go. Now B is 0. So this B will go as it is 0, 1, 0. Output will be 0. Input 1 and 0 will give output as 1. So this will be 1. Now if both of them are 1, so here we'll give 1 directly, and here we'll give, it will become 0. This will become 0. Here we'll give 1. It will become 0. Here we'll give 1. It will be 1. 1, 0. At output will be 0. 0, 0 for OR gate will become 0. So that means this is the truth table for A B bar plus A bar B. So here you can see the output is 0, 1, 1, 0. Here output is 0, 1, 1, 0. That means this logic is equal to this logic. So with this we will stop in this session. Next session we will see few more examples on this. Thank you. Have a good day.